Hi, in this video we're going to look at how to do implicit differentiation. So in the last video we talked a little bit about why we would need to use implicit differentiation, and there's an example of an equation over here where we would need to use implicit differentiation. So the goal would be that we want to find dy dx, but we have some kind of equation where we can't solve the equation for y. So that's when we use implicit differentiation. Okay, so when you do implicit differentiation, there are two main steps, and they're shown over here, step 1 and step 2. There are a couple little details to remember about each one. But the first main step is that you're going to differentiate both sides of the equation with respect to x. And then the second main step is just to use some algebra to isolate dy dx. So at the end you have dy dx equals some expression involving x and baby y also. Okay, so we're going to talk through some details about each of these steps and then also do those steps with this example, and then we'll also look at one more example. Okay, so when we're going to differentiate both sides of the equation with respect to x, one key idea here is that we're going to be treating y as a function of x. Okay, so when I see these y's in the equation, if I'm wanting to find dy dx, then that means I'm thinking of y as being a function of x. Even though we haven't solved for y equals f of x, I'm treating y as a function of x. So when I differentiate both sides of the equation with respect to x, one important idea here is that whenever I differentiate any expressions involving y, we're going to need chain rule. So we'll look at that when we look at this example here. And I might have a little bit more to say about that main bullet point. I don't have this next bullet point in this particular problem, but we will in some of the other examples we look at. If I have any terms in the equation that involve both x and y, then I'm going to need to use either product or quotient rule, or both. Okay, so we won't need that in this particular example, but we'll look at some examples later where we'll need to worry about that. And then the last point about differentiating both sides of the equation with respect to x is to remember that you're doing that to both sides of the equation. Whatever you're doing to one side of the equation, you want to do to the other. It's really common that students will do one side but forget the other. So don't forget to do both sides. Okay, so we're going to do these steps over here on the example we have typed over here to the side. Okay, so we've got an equation where we've got y in the equation, and we can't do algebra to explicitly solve that equation for y, so that I have y equals something completely only in terms of x and no y's over there. So I still need to find dy dx. For whatever reason, I might be interested in a slope of a tangent line or an instantaneous rate of change, and so we're going to use implicit differentiation. Okay, so first main step is differentiate both sides of the equation with respect to x. So I'm going to write this differential operator d dx of both sides. Okay, so I applied that differential operator d dx to both sides of the equation. So that's telling me differentiate with respect to x on both sides of the equation. Okay, so we're just going to go through and do this then. So on the left side, I'm going to find the derivative with respect to x of x cubed. All right, so that's a pretty easy derivative. We just get 3x squared. All right, and then on the next term here, I'm going to find the derivative with respect to x of y. And remember that we're treating y as a function of x, so the derivative of y with respect to x would just be dy dx. That's what it means to differentiate y with respect to x, dy dx. Okay, the next term here, I've got a y, but that y is also inside a tangent function. The y that I have is inside a tangent function. So when I differentiate that term, that's when I'm going to need to use chain rule. So I'm going to start with the derivative of the outer function. Derivative of tangent is secant squared. Leave the inside alone. And then times the derivative of what's inside there. So times the derivative of y with respect to x. So I get this extra factor of dy dx. Alright, so that was using chain rule. I differentiated tangent of y with respect to x. Derivative of the outer function gives me my secant squared, and then times the derivative of what's inside. Okay, I still have the other side of the equation to do here. So derivative with respect to x of 2, derivative of a constant is just 0. Okay, so at this point I have differentiated both sides of the equation with respect to x. Okay, so I'm just going to rewrite that a little bit neater here without my brackets underneath the terms or the factors. Okay, sometimes I see students that like to use y prime instead of dy dx. I've used dy dx here, and that's really my recommendation on these implicit differentiation problems. When you use y prime, it's easy to get that lost in the other y's that are in the equation here. So I'd really recommend using dy dx. And the other thing I want to point out about that step is that those dy dx's came from when I differentiated terms involving y in the original equation. So when I differentiated the y, I got dy dx, and then when I differentiated this term involving y here, the tangent of y, that's when I got an extra dy dx. So over here, when I had written these steps where I said any expressions involving y, you will need chain rule, and when you find those derivatives of expressions involving y, what will happen when you use that chain rule is that you're going to get an extra factor of dy dx. That factor comes from using chain rule. There. Okay, so we did the first main step, differentiate both sides of the equation with respect to x, and now we're going to use this second main step here, use algebra to isolate dy dx. So again, there are a couple of steps that happen with that. I'm going to scroll up just a little bit here so I have room to write some key ideas with that step. But when I use algebra to isolate dy dx, the first thing that you generally want to do is use addition or subtraction. Sometimes there's a little algebra to do before this, but use addition or subtraction to get the terms that involve dy dx on one side of the equation, and the terms that do not involve dy dx on the other side. So I'll just put here the other terms on the other side. So sometimes there's a little bit of distributing through first, but generally you're going to always use addition and subtraction to get terms, move terms from one side of the equation to the other. The next main step there in the algebra is that you're going to factor dy dx out of the terms that involve dy dx. Once you've done that, you'll have dy dx times a bunch of stuff equals some expression that doesn't involve dy dx. And so the last main step is you're going to divide through both sides of the equation by the factor that is times the dy dx after you factor that out. And at that point, you're finished. Okay, so let's go look at the example that we've been working on here up above. I've highlighted the two dy dx's here. The other thing that's important is that you pay attention to terms. Remember that terms in an equation are separated by addition and subtraction signs. So I really have three terms on the left side of this equation. 3x squared is a term, dy dx is a term, and then minus secant squared y dy dx is another term. I just have one term on the right side of the equation that's 0. Okay, so I want to use addition or subtraction to get terms involving dy dx on one side. I already have all the terms that involve dy dx on the left side of the equation, and then the other terms on the other side. So for this one, I'm just going to subtract 3x squared from both sides of the equation with the goal of getting rid of that on the left side. So I'll be left with dy dx minus secant squared y times dy dx equals negative 3x squared. Okay, so I've used addition or subtraction to get all the terms involving dy dx on one side. Now I want to factor out the dy dx. The algebra here is always pretty much the same. Gather the terms on one side of the equation and then factor out dy dx. Be careful here to notice that when I factor dy dx out of this first term, I'm actually left with a 1, not nothing, I'm left with a 1. And then when I factor dy dx out of the second term, I'm going to be left with minus secant squared of y. Okay, and then the last main step here is just to divide through by that factor that's times the dy dx. And that will make that go away, so that at the end here you've solved for dy dx. Okay, so I have this answer here. One thing to note is that sometimes you could do the algebra in different ways, and so depending on the order in which you do the algebra, you might have an answer that looks different but is also equivalent to the answer that you might see in an example or an answer key or something, or the back of the book if you're looking at problems and comparing with answers in the back of the book. So I'm going to just write another equivalent form of this answer. There's a lot of minus signs in this problem that I have, and if I just think about taking the answer that I have in the box here and multiplying by -1 over -1, that's just multiplying by a form of 1, so that will keep it the same. But then my numerator would be positive 3x squared, and on the denominator I would have a -1 plus secant squared of y, or secant squared of y minus 1. So that's also an okay answer. Either one's fine. If you're doing online homework, it should accept either answer or any other correct form of the answer. If you're checking answers in the back of the book, though, or with an answer key, it's just important to understand that they could be written in a slightly different form. So this is kind of a common way that you might have answers different, is just distributing through a -1 on the numerator and a -1 on the denominator, and that will change all the signs. Okay, so we're going to stop this and then do one more video where we look at another slightly more difficult problem, and then several more videos where we look at even more complicated implicit differentiation.